Okay, so today we'll finish chapter 2 on multiple integration. So we have two more things to talk about. One is cylindrical coordinates, and the other is the spherical coordinates. Okay, so last time, towards the end of the lecture, so I started the cylindrical coordinates, right? So you may still remember that the way we define the cylindrical coordinate is actually quite similar to what we had in with the polar coordinate, right? So, but it's just that now we have the third dimension z. Okay, so if we don't worry about the z dimension, the z position of my point, then basically what you have on the xy plane is a polar coordinate. Okay, but just a notation difference is that with the with the polar coordinates, okay, so we have this to be r. Okay, so I think here, as I think maybe I've mentioned last time, is that I have some inconsistent notation here. Is that here I always want to use a rho and this is phi, okay, instead of r and theta. Okay, so let me change off this. So instead of r and theta, okay, so I have rho and phi. Okay, rho and phi. So now we need to look at again is the differential element, right? So in Cartesian coordinates, right? So we have this differential volume element dv is simply given by this dx, dy, dz, right? So this small box here, right? So in cylindrical coordinates, the differential volume elements looks like this. Okay, you can see the shape. Okay, so some of the faces are curved, so it's not exactly a cube. Okay, but let's see how it works. So first of all, what you can see if you just see the top surface of this differential volume element, you'll see that this is exactly the same as what we had in the polar coordinate. Okay, so this the top surface. Okay, so you may still remember that the area of this in polar coordinate is given by r d theta. Right, so here again the area of this surface here is given by rho d rho d phi. Okay. So but now we have the third dimension, the z, right? So basically we just need to add a thickness, right, to this. So then we have this dz. So then the volume of this element is given by this area, right? So times this thickness or this height, right? So then that's why my dv is given by rho d phi dz. Okay. So again, just like in polar coordinate, although you can see that this, right, is not really a rectangle, right? But as we consider this is very small, so when we calculate the area of this surface, we simply use the formula for calculating the area of a rectangle. Okay. So now I know the how to express this dv in this cylindrical coordinates, right? So then of course to be able to do the triple integral, we need to know how to set the limit for all the three coordinates, right? So because as I just mentioned, right, the rho and the phi is basically the same as the r and theta, right, in polar coordinates, right? So then when I set up the rho limit and then the phi limit, right, the idea is exactly the same as what we had in polar coordinate, right? So you can go back to I think it's page 24. This page, right? So might still have the when I set up a fixed row, that means that I'm drawing a circle, right? And then when I'm setting up a bigger row, then I'm setting up another circle which is bigger, right? And then for the two angular limit, right? So you are setting different lines, right? Two straight lines. So the only thing that you need to add at the end is the limit for the z direction, right? So and that one is easy, right? Just as I said, it's just considering the thickness, right, of this region here. Okay. So then I think a very good example to look at is to go back to this one. So go back to this one. Last time we tried this example using Cartesian coordinate. Okay. So for this kind of integration region, right? So this is exactly just a cylinder. You could imagine that it would be much more convenient to do cylindrical coordinate, right? So what we need to do, right? So if we try to, I'm not going to finish the entire calculation process, but the important part again is to how to set up the integration limit properly, right? So because I'm considering a cylindrical region, right? So of radius 1, right? So that's why my row go from 0 to 1. Right? And because it's a full cylinder, so that means I need to go the full circle, right? So that's why my phi limit is from 0 to 2 pi. Then here, right? So it's lying between the two planes, right? Z equals 0 and z equals 1. So that's why my limit for z is 0 and 1. So then, of course, if you want to do this integral, this function f, right? So this function f in this question is given in Cartesian coordinate, right? So you need to convert that one also. So this, but that is easy, right? So first of all, z is just z. X, what is x? Is rho cosine phi, right? So then what you need to do is to do the triple integral for this function here. But one thing you can see that this is more convenient than what we did last time is because now all the limits are just constant, right? And again, when you do the inner integral d rho, right? So you just treat rho as the variable, but you just treat phi as a constant, right? So after doing the first layer, you get a function that depends on phi, right? So that's when you take care of the second integral, right? So and then after the second layer, then you will have a function that only depends on z, right? And then finally you do the last one. So and so this example is an extension for the electric plate that we saw previously. Right? Remember, in previously we have this example that we have a circular uniformly charged plate, right? So we want to find out the electric field, right, at the point above that plate, and at that time we used polar coordinate. Okay, so now instead of a plate with no thickness, right? So now I have this cylinder, right? So with an actual thickness of L. Okay, and then I want to ask the same question: is that if I'm right here, right at the distance h above this charge object, so what is the electric field that I will find? Okay. So essentially, you could see that we know how to do one plate, right, with no thickness. So now that we have a cylinder, right, so the idea is that we are we are considering this cylinder, right, as a collection of many thin plates, right? So basically, could imagine that there are many thin plates just forming a stack, right? So and then each plate, right? Each plate has a thickness of dz, right? So for just one plate, right? We already learned how to do it, right? In the previous example. So now we just need to consider many plates, right? So now, of course, the contribution of different plates are different, right? Because some of the plates are up very high at a very high position, right? So the other is at a very low position, right? So this plate, for example, the plate at the bottom will be very far away from my point, right? But then the plate on top will be much closer to that point. So then the effect due to the plate, right? So closer to my point, of course, is greater, right? So what we need to do is that suppose I consider one of the layer, right? So like this layer. So now I want to ask, right? So for this layer, then I can consider one of the volume element, right? One of the volume element. This one. So you still remember that in the last example, I told you that we just need to consider the z component of the electric field, right? So basically, what I need to do is now I need to consider, right, this small volume, right, carrying some amount of charge, right, and then I need to know, right, the 1 over d square, right? So this d is this length, right? I need to 1 over d square to calculate the electric field, right? And then, but again, I still have this same cosine alpha to telling you that to tell you that I only need the z component of the field, right? So at the end, again, by symmetry, just like the example with the plates, you know that the total field after adding up all the contributions will be pointing to the z direction. So then this is the Coulomb's law, right? Again, is the Coulomb's law considering just this small volume element dV. Right? So now then you just need to convert all these angles, right? So to the and this d, right? So to the variables that we will be using, right? So at the end we will be using rho, phi, and z. Right? So basically these are just considering a triangle, right? To have this expression to be expressed in terms of z or rho or phi. Okay. See that it does not depend on phi because of the cylindrical symmetry. So if you So the difference between this one and the one with the plate without thickness is the dz, right? And also this, right? Because now in the previous example, I only need to know h square plus this horizontal distance square. Now I need to know this distance, right? This distance. This distance is not just h, right? It's h times h plus this depth, right? This depth is given by minus z. Okay. So because I consider this point as the 0, 0, 0. Okay. So and that's why at the end you have to do a triple integral like this. Okay. Again, if you just consider this part, okay, so this is what we had with just one plate with no thickness. Okay. And then as I said in the last example, you just need to set this z equals 0. So then I'll skip the details here, but this is the final answer you got. Okay. Okay. So then the other important coordinate systems that we need to learn is the spherical coordinates. Okay. So this time I have again a point P at the x, y, z. Okay. Again, first I have a Cartesian coordinate system. Then in spherical coordinates, so the three variables that I used to indicate my position of this point P are this R. Okay, so this R is the distance between this point and the origin of the coordinate system. Okay, so this is R. So the second variable is this so-called polar angle theta. Okay. So this angle theta is the angle between this blue line and the z-axis. So it's called the polar angle is because you could imagine if I have a sphere, then what you have on top is this north pole, right? So that's why so because this angle is the angle between this blue line and the axis pointing to the north pole, so that's why this is called the polar angle. So then I have R, I have theta, and then the third one, okay, the phi again is the same. This phi is the same as what we had in the cylindrical coordinate. Is that I project this point P onto the xy plane. Okay, so then I'll be here. Then the angle between this line and this line will be phi. Okay. So you remember that in the cylindrical coordinate, we call this one rho. Right, this line is rho. Okay. So in a spherical coordinate, okay, I don't use this rho anymore. I directly use this distance r. Okay. So now you can see how we can convert from one coordinate system to the other coordinate system, right? So like r, of course, is the square root of x squared plus y squared plus z squared, right? This distance here. And this tangent phi, right, is the ratio between, right, this length and this length. Right, so that's why tangent phi is the ratio between the y coordinate and the x coordinate. Right. So finally, this theta, cosine theta, is the ratio between, right, so the z coordinate and this R. Okay. So, and here just show you how to do the other way, right? So what I just told you just now is from our data file to XYZ, and then you want to go from XYZ to our data file, you follow this formula. So from this geometry is actually not difficult to see how they work. So now I want to do triple integrals, right? So in cylindrical coordinates. So again, I need to figure out my differential element dV. So this is what I will have. So let me explain. So again, you will see that I have some curved surface. Okay, so it's not exactly like a cube. Okay. So the way that we think about this element is the following. Okay, so first of all, you just consider that we start at a point. Okay, this point here. So this is a point that I have a particular value of r, theta, and phi. So then suppose I am at this coordinate, and then I want to change one of the coordinate by infinitesimally small amount while fixing the other two. Right, so for example, the first case I can do from r go to r plus dr, right? But then I fixed the theta and phi to be the same. So then if you do that, then you go from this point, right? You'll be walking along this line, right, to this point. Okay. So let me try to label that. So originally, we are at this black point. Okay. So that's the first way. Okay. So the second way is that you fix, again, you go from the black point, and then you fix your r coordinate. Okay. You fix your phi coordinate, but then you change your theta coordinate a little bit. So that means you go from theta to theta plus d theta. So then in that case, you'll be moving along this circular arc, right? Because your r is fixed, but then you change your theta a little bit, right? So then the trajectory that are formed by my fingertips will be a circular arc. Right? So that's why you'll be walking, you'll be moving along this circular arc, and you'll be here. Okay. So that's the first. This is the second. So finally, if you fix r and you fix theta, but you change your phi coordinate a little bit, then what you'll be doing is that just like my finger here is that you'll be, the trajectory again will be the circular arc, right, formed by the movement of my finger. So that's why you'll be walking along this line here. So again, this is a small circular arc. Okay. So in the second case, right, the circular arc, the length of this circular arc is simply given by r d theta. Okay. But in the third case, okay, we need to be careful. Okay, so the length of this small circular arc is given by r sine theta d phi. So what is this r sine theta? So r sine theta is this. Right, this is r sine theta. And that's why, and this is d phi. So that's why this one is r sine theta times d phi. So now you form 3 lines, and basically these 3 lines give me the 3 dimensions or the 3 edges of the differential volume element. Okay. So again, although you understand that this is not really a cube because this one is curved and this one is curved, but since it's infinitesimally small, and then the way that we define we express the volume of this element is simply using the formula for a cube. Okay, so this or a box. Okay, not exactly a cube. So it's basically the product of the length of the 3 edges. Right, so I have this dr times r d theta times r sine theta d phi. So then that means you have this r square sine theta dr d theta d phi. So this is the differential volume element in spherical coordinates. Okay. So now if you do the integral, right? So we need to again set up the integration limits. So geometrically, how do we visualize this integration limits? Okay. So let's consider the 3 of the variables, 3 variables one by one. Okay. First, again, I have this bracket is for you to put your function, but we don't care about what exactly that function that you want to integrate, right? So I just want to consider the integration limit. So first, if I consider the limit for the r coordinates. Okay. So if I go from 0 to r, so that means I'm going from this point, right? So the 0 is basically just at origin, and then r this r naught is go from here to some value r naught here, right? So but as long as I don't specify the angular limit, so basically you are free to pick any direction to go, right? So as long as you go your distance, right, between the origin and your point is r naught, then that's okay. So that's why a constant boundary of r, so I call this r naught, right, is basically defined by a spherical shell. A spherical shell. You can be at any point on this shell. Okay. Any point on this shell satisfy this. So a constant boundary of r is defined by a spherical shell. So now for the theta, the polar angle. Okay. Right. So remember the theta is the angle from the North Pole, right, to your point. So again, if you 0, so 0 just means that you are exactly at the North Pole, right? So any point, basically that means any point along the z-axis, right? So this is not straight enough, but this is a North Pole. But if you theta equals 0, so that then you can be any point along this line. So now if I am at theta equals theta naught, okay. So what it means is that I have this cone, and then the angle between the edge, the cone, and the North Pole or the z-axis is theta naught. Okay. So that means the boundary, this theta naught boundary forms this cone. Okay. So you can be anywhere in this cone. Okay. But notice that, okay, so this cone actually extend to infinity. Okay. So because at this step I did not specify anything about the R, right? So the way that we specify R is over here. But here, if I don't consider any a limit for the R, right? So then basically that means that you can be at any point on this cone surface, right? So but this cone can extend to R equals infinity. So then from 0 to theta naught, right? So you're free to be at any point inside this cone. Okay. So finally, for phi, right? The phi. So actually, theta is called the polar angle, right? So phi is known as the azimuthal angle. Okay. So for phi, so again, I start from 0. So 0 means that you are on this red plane. Okay. So this plane is actually, yeah, this plane. So this plane is lying on the x equals 0, right? So this plane is parallel to the x axis. Okay, so that's why this red plane is the phi equals 0 plane, right? So again, notice that this plane extend to upside and up and down to infinity, right? So you can go to positive x direction, right? And then go to negative x direction, right, for an infinite distance. Okay. So now I have the upper limit, the second plane is this blue plane. Okay, so this blue plane, I have this phi equals phi naught. So what is this phi naught? So this is phi naught, right? So again, this plane is infinitely big. Okay. So then if I specify this integration limit, again, in this case, I did not say anything about the other two variables. So in that case, so that means you are talking about the entire region, right, between these two planes. Okay, the entire region could go up to positive x infinity, negative x infinity. And also you can go this way to infinity also. But you have to be between these two planes. Okay. So now, of course, at the end, I need to combine the effects of all the boundary, right? So 3 examples. So if I, so you could imagine that if I from 0, if my theta naught is 2 pi. So what you could imagine is that this angle is, I'm sorry, not 2 pi. So this angle is basically like this, right? So you are considering from the North Pole all the way to the South Pole, right? Because if your theta is very large, right? If it is very close to 180 degrees, right? So you actually have a cone that like this. So this is not exactly 180 degrees yet, but let's say very close. Then you draw a cone like this. So basically, so any region up here is your integration limit. So that's why if you have this data not to be exactly 180 exactly pi, so then you are considering the entire entire region here, right? So that's why if you want to integrate the entire sphere region, right? So the theta you have to go from 0 to pi. Okay. And here you can see that my R does not go from 0 to 1. Let's say if I go from 1/2 to 1, then that means I need to draw two a spherical shell, right? So one is the one inside, the smaller one, and then the other is the bigger one. So then you are then we are talking about the region, right, in between the two surfaces, right? So this region, right? So from 0 to pi, so I'm considering from North Pole all the way to the South Pole. And then here the phi, I go from 0 to 2 pi. So that means I have to consider a complete circle, right, in the XY plane. So now if I have this second case that I have the data limit go from 0 to pi over 6, then what I have is I have to consider, right, so the intersection between this spherical shell, and this cone, right? So then you are only talking about this region here. So then in this case, the third case, okay, so if I consider from 0 to 1 and then 0 to pi, but if I only consider from the phi from 0 to pi over 4, and that means, so if I don't have the 0 to pi over 4, then I have if I have the 2 pi, then I have the entire spherical region, right? But because you only have them from 0 to pi over 4, then we are only talking about this slide. Okay, so just like cutting a melon, right, into many pieces, right? So you're only talking about this region, right, between this red and the green plane. So here is an example. So suppose I want to find I have a sphere. Okay, I have a sphere, and then of radius r, and then this is the density profile of the sphere. Okay, so you could see that for this sphere at r equals 0, the density is the highest, and then you go to the outer part of the sphere, then the density is getting smaller and smaller. Okay. So suppose I have this sphere, okay, and then I want to find out the mass, right? So basically, what do I need to do? I need to do the triple integral, right, of this density function, right? So over the entire sphere. So for a small region of this mass, okay, so within a tiny volume element of that sphere, then the mass is given by the density, right, times the small volume dV, right? And this dV, you know what it is that r square sine theta dr d theta d phi. Right? So then if I want to find the total mass, right, I need to integrate over the entire sphere. Right, so if you want to integrate over the entire sphere, you need to go from the r limit from 0 to r, right, and then the theta limit from 0 to pi, and then the phi limit from 0 to 2 pi. So again, this is actually is quite easy to do, because you can see that first of all, this integrand, right, does not depend on phi at all, right? So that's why the integrate over phi will just give me a factor of 2 pi. And also, when you consider the first and the second layer for the integral, right? So you realize that your integrand can be written as a product of the function of just r only, and then a function of theta only. So remember, that means you can treat this as a product of the two integrals, right? The product for the integral for r and the integral for theta. And then if you integrate over the theta from 0 to pi, right? So this one just give me a constant. Okay, it's just actually just 2, right? So that's why this theta integration over theta give me 2, and then integration over the phi give me 2 pi. So that's why I have this 4 pi factor up front. So, and this rho naught is just it's always there, just from this function. So all I need to slightly worry about is this integral for r, and this is also straightforward, of course. And then at the end, you just get a result. So this another example that you'll find it useful even in the next chapter, is that when we do not the integration over the volume, but if I want to just do some what we'll call the surface integral. So, but I'll talk more about that later. But here, you see what I want to do is that I want to evaluate, okay, the surface area of this yellow portion of the sphere. So if I take the cross section of this sphere, so this is what I have. Okay, so basically the edge of this yellow region is here. So this is making an angle theta naught. So if I want to do this surface area, what I need to do, you could imagine that again, I'm trying to consider very, very small sections. But this time, I don't need to do dV, right? Because I only need to do the area element. So this is what we want this time is dA, not dV. Okay. And from here, from this picture, right? If you just take this small section out, right? What you have is actually this outer surface of this dV. Okay, this outer surface of this volume element dV. So therefore, my dA is actually this area. Okay, this area. So, and for dV, we have r square sine theta d theta d sine theta dr d theta d phi. Right. So then, because I'm not considering the volume, I don't need this dr. So then that's why this is my element for the area. Okay. R square sine theta d theta d phi. Okay, this area here. So now, if I want to calculate the surface area, right? So the polar angle, right? You understand that I need to go from 0 to up to here, the theta naught. Okay. And then for the xy plane, I need to complete the full circle. So that's why again I need to go from 0 to 2 pi, right? So and at the end you'll find that the answer is 2 pi r square 1 minus cosine theta naught. Okay. And for the special case that we are familiar with, right? So if you have this data not set to be pi, so then that means you are considering the surface area of the entire sphere, right? So then 1 minus cosine theta naught is 2, right? So then you have your 4 pi r squared. So finally, it just say a few words about this so-called Jacobian of transformation. So it won't be in the exam, won't be in the homework. Okay, but this is a concept that you might revisit later. Okay. So remember, in 2D or 3D, we have been considering coordinates from one coordinates to the other coordinate. Right? So for the 2D, right, we go from this Cartesian coordinates, right? So and then we go to the other coordinate known as this polar coordinate. And then we found that the form for this differential area element are not the same. Right? So this is just dx dy, but after you go to polar coordinates, you don't just have dr theta, right? You have this r dr theta. And we understand how it works by considering the geometry, right? By seeing the picture of this differential area element. Okay. So, but that's a systematic way that help us to figure out this factor of r, okay, without relying on the geometry. Okay. So because what we are doing here is a change of variable, right? Geometrically is a coordinate transformation. Okay. And mathematically is a change of variable. So remember that when you learn about the integration for just one variable function, but we have also done a change of variable before, right? So if you let the new variable u, right? So then the formula for you to re-express your integral is like this, right? So this is something that you have done before, right? So now what we are doing is also variable change, right? But with a pair of variable, And it turns out that there is just a formula that we can use to make this variable change and figure out the extra factor that you need, right, after you do the change of variable. Right? So we in this integration for one variable function, right? So after you do the change of variable, you have this extra factor dx du here. So here, right, from a pair of variable uv, right, to another pair of variable rs. So you could think of uv as xy. You could think of rs as r and theta. Right? So when we do that, there will be an extra factor here. Okay, and this extra factor, okay, is actually known as the Jacobian. The Jacobian, okay, you sometimes people use this to denote the Jacobian, and what it really means is actually a determinant, a 2x2 determinant. Okay, and so what you can try is that if you set your u to be x, right, v to be your y, so r to be your r and s to be your theta, and you know how xy related to r theta, right? So you are able to do this 4 partial derivatives. And if you try to do this, right, so you can try to verify that this this Jacobian, okay, is indeed give you the factor r. Okay. So I won't say too much about this here, but for further reading, okay, so you can go to this book, okay, to understand why it works, how it works, and also if you, of course, this can be generalized, right? So just like in 3 dimensions, right? When you go from Cartesian coordinate 3D to spherical coordinates, right? So what you have now will be a 3x3 determinant, okay, instead of the 2x2 determinant. Again, you can refer to this book for more details. Okay. Okay, so this is the end of chapter 2. Okay, so now let's take a 10 minutes break. We'll come back at 12:30, and then we'll start the new chapter, chapter 3. Okay. We'll come back at 12:30. Okay. Okay, so now here we come to chapter 3 on vector calculus. So what we have done in the first 2 chapters are functions which are scalar. Okay, so here we'll be talking about functions, but they are vector valued functions. So remember in the last 2 chapters, we have this example of this temperature distribution of air in a room, right? So, and this is an example for this scalar function, or I call it a scalar field. Okay, so for each position in space, right? So you give me a number, right? The scalar. So then that describes the temperature at that point. Okay. And then we have learned the partial derivatives and then the integration. Right? So we understand that the meaning of taking partial derivative is that if we go from one point to the neighboring point nearby, right? So we are looking for how much change that we have. And then for the integration, right? So basically what we are doing, for example, in an example, in a question that we try to consider is that we want to find out the average temperature, for example, right? So, or if we have some density profile of a mass object where we want to find out the mass, right? So we are adding up the scalar values over a big region that we are considering. So that's what we have considered over the first 2 chapters. So here we are going to consider a vector value function, or call it a vector field. Okay. So again, you can consider a room, okay, and then air flows in the room, and then suppose at different region in that room, okay, so we have different velocity for the airflow. Okay, so then if I want to describe the velocity distribution of the airflows, right? So at different parts of the room, so we need a vector field, right? So at each point right? So you need to tell me the not just the magnitude of the velocity, right, and also the direction. So, or of course, other examples will be electric field, right? So I put a charge somewhere, and then the neighboring region, right? So you'll find you'll be able to detect electric field, right? So for electric field at each point, right? So you need to tell me the direction and also the magnitude. Essentially, so each point in the space, right? So you need to give me a vector, not just a number, a scalar, to characterize the situation at that point. So that's why the roughly speaking, okay, so the reason why we need this vector calculus is because now we also need to describe, right, the change and the sum of this vector field. Okay, but now I not only that I want to describe the change of the magnitude of the vector, I also want to describe the change of the direction. Okay, and also when I do the sum, okay, I not just that I want to describe the sum of the magnitude of the vectors, but also the direction. So here I give you some simple vector valued function or vector fields in 2 dimensions. Okay, so we'll be considering 3 dimensions later. But let's say I consider the XY plane, and then here I have 4 different vector fields. Okay, so you can see that what I have here is that if you give me the x coordinate and then the y coordinates, okay, then this function f, this vector function f, will give you a vector at that point. All right, so let's say, for example, if you just give me 0, 0, and then what you have here in this example is a 0 x hat plus 0 y hat. Then in the middle, you see that there's no arrow here. The arrow is just a 0 arrow. So now if you give me a number, for example, 1 and 0, right, so that means you are at this point. So then the vector I give you will be x hat plus 0 y hat. So you can see that it's a vector pointing this way. So just one remark, maybe you are more familiar with this I hat and j hat and k hat, but this is the x hat that I'm talking about is just the I, and then the y hat is just the j. Okay, so instead of using I, j, k, I'm using x hat, y hat, and z hat. Yeah. So then here you can see that for different points in this xy plane, so I can draw an arrow. So then of course in principle the space that I don't have an arrow does not mean that there's 0. It's just because I'm not drawing too many of them. Right? So in principle, okay, every point in space, right, so you need to draw an arrow. But just like in chapter 1, when I draw the gradient, you remember the gradient that I have all the vectors. So we can just practically we cannot draw too many. Okay. So now if I consider the second example, okay, so this vector field is very similar to this one, except that you have a minus sign in front. Now the difference between this one and this one is just that here you can see that the vectors are always pointing away, right, from the origin. But here, because of the minus sign, the reverse direction for all the vectors. So they are all pointing towards the origin. So now if I have this third example, so this is this y x hat minus x y hat. So what you see is that the vector field. So one thing is still the same as the last 2 cases, that the further away you go from the origin, the longer the vector you get. So that means the magnitude will increase as you go further and further away. But here you can see that the direction of these vectors, okay, so they are not pointing away from the origin. Instead, they are circulating like this. So in the last example, so I add the minus sign in front, then you can see that it's also circulating, but this one is clockwise, this one is counterclockwise. Okay. So now I have these four examples. So four of them, they have the one thing they are the same is that the magnitude of the vector field the same. Okay, so because this one is x squared plus y squared square root, this one is minus x squared plus minus y squared square root, and this one y squared plus minus x squared square root, but all of them will give you the same the same magnitude. Okay, so you can see that. But of course they are all different, right? In the sense that, right, the directions are all different. So then when we consider these vector fields, there will be two questions that we try to ask. Okay, so suppose I pick a region. So let's say this red region here. I want to ask, is there a net outflow or inflow? What does it mean? So if you imagine that these are air flow, right? So in this case, you tell me that, okay, so the airs are flowing into this region, right? So, and on the other hand, you ask me about this one, so you tell me that the airs are flowing out. So that's what we physically mean outflow, flow, or inflow. And the other questions that we'll ask is whether it's circulating, like this one or this one. Okay. So we have some calculus tools to characterize these two behaviors. So before we actually go to that, the first calculus tools that I'm going to introduce is known as the line integral. Okay. I believe you have seen line integrals in mechanics, maybe when you calculate the work done of the force on a particle. Right? So what I have here, suppose I have a vector field. Okay, a vector field. So imagine that this vector field is a force field. Okay, so that means these arrows represent the force that experienced by a particle that you put on it. So now suppose I have this, so the particle that goes from this point P, okay, with this initial coordinate x naught, y naught, and then eventually move along this path to the endpoint Q. Okay, so suppose I consider this situation here. So now what I want to ask eventually is over this path. Okay, so what is the work done by this force field on the particle? Okay. So of course, physically you might ask, okay, if the force is like this, then it doesn't seem that the particle should move in this path. But what we don't consider, what we don't really tell you here is that physically, if this move like this, of course, we will need some kind of external force to guide the particle like this. Right? So the external force by us, let's say, but that is not the part that we care about. Right? So at the end, I don't care what kind of total force that we need for the particle to go from P to point Q like this. Right? So, but I only care that now I give you this path. What is the work done on this particle by the vector, this force field? Okay. So, and when we do that, what we need to do is that we consider many small steps made by this particle. Right? So for each step, okay, the force experienced by the particle will not be the same. Right? So when it's here, you can see that the force is greater, and in this direction, when it's here, you can see that the force is smaller, but direction is not the same. Right? So you need to consider each step. So let's say we consider a particular step. So from here to here. So from here to here, I call this delta R. So delta R is given by the difference between the position vector of this particle at this t plus delta t, okay, minus, right, the position vector of this particle at t. Okay. Position vector at t plus delta t, position vector at t. So this is the infinitesimally small amount of displacement that is made between t to t plus delta t. Then at this position, right, so we know the force, right, by substituting the value of coordinates to this force field function. So then the line integral, the line integral, okay, from P to Q, right, is defined at this sum. So, and each time you only make a very small step, and it is written as this integral. Okay. So this is the first thing that we want to learn how to do. Okay, the line integral for this force field, or for this vector field F. Okay. So of course, physically, I'm talking about work done, right? Because this is the example that for you to easy to think about, but in principle, even it's not a force field, right? So any vector field, I can define this line integral like this, right? Even it physically might not be referring to work done. Okay. So now what we need to do, okay, so is the following. Okay. So first of all, if I have this path like this, I need to tell you how to mathematically describe this path. Okay, this path. So this path is basically given, right, by the head of this position vector arrow, right, as a function of time. So then suppose the position vector of this particle r of t is written like this. Okay. X of t is some function, and y of t is some function. And at the end, so of course you need to pick x and t and y of t such that it makes this path. Okay. I'll talk about some specific type of path. But here, let's say I have these two functions here. And then you just imagine that at t equals t0, okay, the position of the particle is here. Okay. And then at t equals t1, okay, the particle is at this x1, y1. So now the force, right, the vector field is given already. Right, so if I want to find the force experienced by the particle, right, so as a function of t, then I need to substitute this x of t and y of t into this function here. Okay. So then at t, the force is given by this. So basically, what we are doing here is that from x and y, right? So we imagine that is both x and y are function of t. So physically, you could think of it as time, right? So, but mathematically, this is what we call a parameterization. Okay, so I want to describe this curve, then that means x and y are related, right? And then x and y are related through this t. So now, from the original definition, right? So the integral, the line integral is the integral f dot dr. Okay. And now this dr, okay, can be written as, this is just a chain rule, is that can be written as this dr dt times dt. So basically, you could treat this as v, right? So dr equals to v times dt. So then if I just explicitly write out all the terms, like this dot product, where the x component times the x component of this, plus the y component of this times the y component of this, then this is what you will have here. So let's have some example here. Is that suppose if I want to have a path that is just a straight line. Okay, so starting from -1, -1 to 1, 1. So then you know that the r can be expressed as this t x hat plus t y hat. Okay, because if it's on this straight path, what it means is that y is always equal to x. So this x coordinate and this x position and y position always have the same value. So then I can make this parameterization. So r is t x hat plus t y hat. And then of course I need to also specify my time interval, right? So because it starts from -1, -1, and then I end at this 1, 1. Then that's why my t go from -1 to 1. So you could imagine that this is not the only choice, right? Can I have can I say r equals 2t x hat plus 2t y hat? So if I do it this way, it also works, right? Because here the x value same as this y value. But now my time interval, my t interval has to change, right? So then you need to go from minus 0.5. Right? So then you have to do minus 0.5, right, to 0.5. If you want to put this one as your r as a function of t, and you realize that no matter you pick this one or this one, the line integral, the integral f dot dr that you calculate at the end, well, should be the same. So now, if I want to consider another kind of path that we'll use a lot, a circular path. Okay, so what you can do is to do x equals the radius times cosine t, and then the y equals the radius times sine t. Okay. So this is also something very standard, I believe. Right. So because you just put this 0.5 cosine t here, and then this 0.5 sine t here, then you have 0.5 square, well, cosine square t plus sine square t, and that is 1. Right. So that's why we satisfy this path. So then what I just do now is the parameterization of path, right? So I have this curve, the trajectory of this particle in the XY plane, right? Now, suppose I don't want to rely on this parameter T. Okay, I just tell you that, okay, this P to Q, okay, this path can be described by this curve y equals f of x, so this path. So instead of relying on parameterization, let's say if I don't want to do that, okay, that's also okay. So what you need to do is just that your f, your force is still put here, but this time, right, my dr, right, instead of writing dr to be dr dt, right, times dt, here I simply write dr to be dx x hat plus dy y hat. Okay. So then, if I do that, then I actually calculate this dot product. Then I have these two terms here. So, and I can further rewrite this, the whole thing, right, as an integral of dx, but then I have this dy dx to take care of. Okay. So then I just need to do this dy dx, and then I'll be able to know my integral. So then this is just slightly different from what we do here, right? So here we have to rely on dx dt and dy dt, and then integrate over dt. But here, if I want to just integrate over dx, right? So you just have to take care of this dy dx. So similarly, if the path, right, I do not write the path as y equals f of x, but I want to write as x equals g of y. Okay, so then you can follow the same procedure. You find that this path integral can be written as an integral over dy, right, with this integral. So here, let's try to actually do a few examples on the line integral. Okay, so again, this is a vector field that I showed you earlier, okay, this circulating one. And then I want to consider particles go from this P to Q. Okay, so from this 0.5 minus 0.5, and then to 0.5, 0.5. So if I want to do, first of all, I want to do the parameterization, right? Express my position vector, the position vector of this particle, right? The position vector of this particle. Right, this is my R of T. Right, initially R of T is pointing to this way, and then this R of T just keeps sweeping across this line and then goes here. So then you can see that my R of T, of course, my x component would be always just given by 0.5, because the x coordinate is not changing. And then, but my y coordinate will be changing. So that's why the y component of this R of T is minus 0.5 plus t. Okay, and let's say here we have t equals 0, and then here we have t equals 1. So again, if you don't like this, right, so you can simply say this is equal to t. However, my limit has to go from, right, 0.5 minus 0.5 to 0.5. So, but at the end, as you calculate the line integral, either way give you the same result. Okay. So then this is my r as a function of t. Then this is, I just write x t to be the x component of my r vector, and then this rt as my y component of this r vector. So then what I do here is exactly follow the definition. Okay, this line integral. Okay, just use this chain rule written as this f dot dr dt dt. Okay. And then remember, so if I do this dot product, this dot product, the x component of f times the x component of this dr dt given here, and then plus the y component of f times the y component of this. So here. So dx dt and dy dt can be obtained from here, right? And then what is this m and this m? This m is the x component of this vector field f, which is this one. And then this n is the y component of the vector field, which is this one. And then dx dt, of course, is just 0, right? And then this dy dt, right? This dy dt given here, 1. So at the end, you'll find the answer here. So now I went from P to Q. Okay, so I do another just very similar example. Now I go from Q to R. So to go from Q to R, you could see that again. I need to consider first the R as a function of T. Right. So this time, my y coordinate not changing, right? So that's why I have this 0.5 y hat here, and then my x go from 0.5 to minus 0.5. Then I can parameterize this x component like this, right? So if you try to put t equals 0, this 0.5 minus t is give you 0.5. And then if I put t equals 1, then this 0.5 minus t give me this minus 0.5. So that's why this parameterization works. So then this is just a very similar example here. It's very similar. So now this would be a more this is a little bit more difficult example here. Okay, so what we have here again, okay, is this vector field. This vector field itself is not very difficult, but here the line, okay, the line that I have is not just go along the x-axis or y-axis. Instead, I'm going at a slope. Okay, so from this 2, 0 to 0, 2. So if I draw a coordinate system, right, so then I go from this point to this point. So then, of course, the idea is, or the procedure is exactly the same, right? So first, you need to find out the r as a function of t, right? So from this point to this point, right? So you can see that you can see that this going up and then going to the left. So after you do the parameterization, okay, right, so again, you just take the dot product, okay, with the force, and then you find the line integral. So in this example, okay, so now I have this circle. Okay, remember how do we do the circle? I have the circle, then I need to remember that whenever I see a circle, right? So then you know that the parameterization that you do is the cosine and sine. Right? So x would be, so you have to have something like this. So but here you don't go the full circle, right? So you just go a quarter of the circle. So go from here to here. So that means the t, when you set the t, right? So you need to just go from 0 to pi over 2. So and that's why after you do the parameterization, okay, so then you have this position vector, right? So as a function of t. Okay. But again, the same idea, right? So after you find the r, and then you also the node, the f is given just in the previous example, and then at the end you are going to do f dot drdt. So express everything in terms of t, right? Express everything in terms of t, and then do the integral over t, right? So, and then the t limit, right, always given by your time interval here, 0 to pi over 2. Okay. So now, if I want to keep going, okay, so if I just now I did 2 paths, right? So from P to Q, from Q to R, although the calculation method is exactly the same, right? So you imagine that you can keep going, right? From Q to R, and then from R to S, from S back to P. So here you can form a closed loop. So I want to consider the case where my path is a closed loop, right? So I have, suppose I call this closed loop, right, formed by this square path C. I call this C. And you understand that if I want to find the line integral over this closed loop, you are going to do the line integrals for 4 times, right? If it's a square. So, right, from P to Q, you know how to do. From Q to R, we also talk about it, right? So then you could just use the same procedure to go from R to S, and then from S to P. So when we have this kind of integral, the line integral around this closed loop, okay, so we'll add this circle symbol, okay, for the integral sign. Okay, so that's just a convention. When you go to, again, when you go to the E and M, right, when you integrate the line integral for closed loop, you'll see this again. So then if I have this circular loop, so this circular loop is not new, I talked about it already, right? So if I actually do it, and then if I do the circular closed loop, I don't need to divide the path into 4 parts, right? Because I just need one parameterization to the cosine t and the sine t to describe this trajectory. Right? So if I do that, right, so I also get this number here. So in this example, you see that I get some non-zero number. Okay, I get some non-zero number. However, if you try the same thing, okay, with this field, so you find that the number that you get is 0. So basically, you might think about why is it the case, right? I'm talking about the work done, right? So you have a particle that go around this loop, right? So you could see that all the vectors at any point are always pointing perpendicular to the circle, right? So that's why if you ask the line integral or the work done, right? So around this closed loop, right, then it's not surprising that you get a 0 result. Right? The force is always perpendicular to your direction of your movement. But on the other hand, if you do this, then it's not surprising that you get some non-zero result, right? So as you go along, right, so you can see that the force is always along this circle. It's always tangential to this circle, right? So that means that as you go, the force keep pushing and pushing your particle along this circle. So then it's not surprising that in this case, you have non-zero result. Okay, but in this case, you have 0 result. So then if I just try to do this all 4 vector fields that I show you in the beginning of the chapter, you see that, okay, these 2 cases I have 0, and these 2 cases I have non-zero. Okay, so just think about the work done, as I said. Here, you see that the result is off by a minus sign with that, right? Because here, as you go, where the force is always pushing you, but here pushing you to go forward, right? But here, if you go along this, right, so you can see that the direction of this vectors always go against you. So then it is not surprising that you get a negative number. Okay. So then next time we'll talk about so that now we know that there's difference. Okay, so some vector field, if you do the integral around the closed loop, you get 0 result. So some of them non-zero. So we'll be trying to characterize the difference, okay, between these 2 types of field. Okay. Okay, so today I think it's a good point for me to stop here.